So we have Norbert Schuch from the University of Vienna talking about entanglement in quantum information theory.
Thanks, Ignacio. Thanks to the organizers for having me here. So I was asked to talk about quantum information theory, and since this is a very general topic, I was wondering which aspect of quantum information theory I should focus on, and I felt like a common theme in this workshop, and the people in this workshop, is to look at entanglement in quantum systems. And so entanglement is really something which, in some sense, is a very central subject in quantum information theory, the study of entanglement. And what I would like, I mean, you know, as a quantum information person, you listen to people, they always compute entropies, and they say that's the entanglement entropy. And what I would like to clarify is really what do people mean by entanglement in quantum information theory when they say entanglement? And how does the entropy show up? What meaning does it have? Why do people in quantum information theory say it's a very good way to measure entanglement? And what are the limitations? Because it's not like a universal tool to measure entanglement in every situation. It's actually pretty tailored. And I think it's also important to be aware of the restrictions of the entanglement entropy, and that it's not like a Swiss knife which fits everything, but a very specialized, very powerful tool for a specific setting. Right. So when we look at entanglement, what we look at is a quantum system which is divided between two or several parties. So we split up a quantum system to several parties. And in my lecture, I would like to focus on what we call the bipartite setting. Meaning that we have a quantum system which consists of two parts. Let me put this here because I would like to refer to this picture later. So we have a system of Alice who has some Hilbert space, and I will look at finite dimensional Hilbert spaces here. And we have Bob who has his Hilbert space H Bob. And so if you would like to know about more qubits, I have 3 discussion leaders for the discussion groups, which are Ignacio Sirac, Frank Fastrate, and Barbara Kraus, who are experts on 3 qubits, 4 qubits, and many qubits, respectively. So you can ask them about all these things in detail. So I will focus on the bipartite setting because, well, first of all, many things become already clear here. Second, one can make much stronger statements because it's more structured. So what does it mean to have this setting in quantum information theory? Well, it basically means that the two parties, Alice and Bob, are restricted in what they can do, or we, as someone studying this, assume certain restrictions in the manipulations we can do to the system. And this restriction is called LOCC, which stands for local operations. And classical communication. So we assume that Alice can do everything to her quantum system in Hilbert space HA. Bob can do whatever he wants to do to his quantum system. And they can exchange classical messages, because the idea is we want to know what the quantumness of this situation is. Where do quantum effects enter? Classical communication is cheap. This is also something which is kind of a realistic setting typically, right? That exchanging classical messages is much easier than sending quantum states around reliably. So what does LOCC mean? Well, it means that, say, Alice can start by doing a measurement on her system. So she will implement some measurement. She gets some so Alice and Bob share some quantum system, which could be some pure or some mixed state. So Alice does some operation. She gets some outcome I, and she sends this classical outcome, which I indicate by a double line, to Bob. Now Bob can do some operation to his part of the system. And this operation Bob does will depend potentially on the information he gets from Alice. Right, so this will depend on I. And Bob will get some outcome J, and he will send this outcome J to Alice, and also keep a copy of the outcome for himself, of course. So Alice will do a measurement which will now depend on I and J. And we can continue like that until at some point Alice and Bob stop and say, OK, we achieved something. And we would like to study what can they achieve, what are the limitations of what they can achieve. And the thing is, we're not imposing any limit on the number of rounds. which is something which makes this in principle very complicated to study, because there could be an arbitrary number of rounds, so we have to look at some kind of closure in the end if we want to know all possible operations which Alice and Bob can carry out in the system. Now, why is this interesting? Well, the interest comes from the fact that not all transformations are possible in such a setting. Some transformations will be completely impossible. Right, so this is a restriction. Which means not all transformations can be carried out. And say if Alice and Bob start from individual quantum states in their labs, right, so they don't have any entangled state at their disposal, they might also not be able to prepare any quantum state they want, right? They have a product state, they do measurements, it will still be a product state. Communicating results can only build up classical correlations. So not all states can be prepared. So in particular, if there are states which we can't prepare in such a setting starting from a product state, so I should say I will also focus on pure states in this talk. So psi cannot be prepared from something like a product state of some initial state on Alice's and on Bob's system. Then we say that the state psi is entangled. Now, an interesting thing, and this is part of the quantum information perspective. So one thing is if I impose restrictions on what I can do, certain quantum states, which were before just some arbitrary state in this joint Hilbert space of Alice and Bob, suddenly become interesting quantum states or different quantum states in the sense that I can't just prepare them, right? I cannot just apply a transformation which prepares such a state. Now, the interesting thing is that on the other hand, precisely those states are something which allow us to overcome such restrictions, which is what we would call a resource perspective. So in particular, there is, you probably heard of that, teleportation, quantum teleportation. So what does teleportation do? Well, basically, what happens is that if Alice and Bob share some quantum state 0, 0 plus 1, 1 over square root of 2, say, and Bob has some other quantum system here, which could be part of a bigger quantum system, then Alice here on the left can do some measurement, namely a measurement in the basis of the 4 Bell states. And if she communicates the outcome to Bob, Bob can apply a transformation, a unitary, such that after this transformation, he is in possession of whatever this quantum system held. And due to linearity, this will also apply if this is a part of a bigger quantum system. So effectively, this will take this quantum system and transport it to Bob. Now, why is this interesting? Well, it's interesting for many reasons, but one reason why it's interesting is because this way we can overcome the restrictions which we have from these local operations and classical communication. Right? So using this, we can in principle overcome the LOCC restrictions. So for instance, if Alice and Bob want to prepare some general quantum state starting from a product state, if they have this entangled state at their disposal, what they can do is that Alice prepares whatever state they want to set up. Then they have this 0, 0 plus 1, 1 state. Alice will apply this measurement and communicate the result to Bob. And what will happen is that this quantum system is basically moved to Bob's side. So they will be left afterwards with precisely that quantum state psi. All right, so they can prepare any state they want if they have this specific entangled state at their disposal. Similarly, if Alice and Bob want to implement a general unitary operation, which they can't do in this LOCC framework, what they can do is that, say, Bob takes his quantum system and teleports it to Alice. Alice implements the unitary operation locally and teleports the system back to Bob, right? So effectively, they have managed to do some general global unitary transformation by using the entanglement. So one can also do other tasks which allow to overcome restrictions. So the point is that what we say is that entanglement is a resource where resource means it allows us to overcome certain restrictions. It enables us to do things. But the interesting thing is that the things it enables us to do are only interesting because we put these restrictions in the first place. Right? So in some sense, the picture you should have in mind is that there is a restriction like LOCC. It gives rise to some interesting states and operations, in particular to entanglement or entangled states. But precisely this thing is, again, what allows you to circumvent these restrictions. So it allows you to overcome these restrictions. So it's a resource. So in some sense, you're making the whole landscape more interesting by putting constraints on what you can do. Suddenly things which before were just simple become interesting. And this is a more general thing, which is also studied in quantum information theory, so-called resource theory. So you could put other restrictions on the operations you could do, right? You could say, I can only do particle number preserving operations. Can I nevertheless measure in a basis which has a superposition of different particle numbers? And then some state which implements such a superposition would enable you to do these things. So it's a more general setting. Whenever you put restrictions, you get interesting states, interesting operations, and then you can try to see how they allow you to circumvent these restrictions. And the goal of entanglement theory is to understand in which way such entangled states are useful and interesting. So to characterize what they are good for, so we want to characterize and quantify the entanglement, which really means to characterize and quantify their resource character, their power as a resource. And of course, this depends on the task we want to do, right? If I want to prepare a specific quantum state, having exactly that quantum state will make it the best resource possible for that specific preparation. But of course, that could be very specialized, right? So ideally, we want to understand, is something a resource for a very general task, like the preparation of any kind of quantum state or the implementation of any kind of operation. OK, questions as of now? Feel free to ask any time. OK. So what we would like to understand is what characterizes states. And as I said, I will focus on pure states under this LOCC restriction here. So the first thing we can look at is a stronger restriction, which will already help to clean up the landscape a bit. And so the first restriction we consider, it's hard physical work. You know, you do it once, you think it's easy, but after a few times. OK, so the first restriction is a stronger one, namely local unitaries. That's part 2, local unitaries. So one thing Alice and Bob can certainly do is to do local rotations. If you wish, we just redefine their local bases. This is special because it's reversible. Whenever Alice and Bob apply a local rotation, this could be part of a measurement, right? One measurement is one where you just do a local operation and you don't measure at all. It just is a one outcome measurement, if you wish. So local unitaries, or short LU, it's a subset of LOCC. So we can start by studying the entanglement under the subset of relations, right? It's basically an equivalence relation. And then we can go on from there. And once we understand what local unitaries tell us about entanglement, we can kind of look at additional operations, namely in particular the measurements. So if we have a general quantum state on two parts, so I pick some basis for Alice and for Bob, A and B, and I just expand the state in that basis. It's a finite dimensional space, right? So C is just a matrix. Then what we can do is we can take the singular value decomposition of this matrix C. So we can write C equal U times D times V, where D is a square diagonal matrix and U and V are isometries or the adjoint of an isometry. So U embeds to a big space to the left and V embeds unitarily into a big space to the right. And then this means that Cij is sum over K. Did I want to call it D? Yeah. Uik. Then the entries of D has positive entries on the diagonal. I call them square root of pk. And then there is vkj. And then I can just substitute this here in my C. So what I get is that my state here is of the form sum over ijk. Now, if I take the sum over I here, right, this is just sum over k, square root of pk. And then there is sum over I, uiki, sum over j, vkj, j. What do I have? Well, this is just, well, an isometry, which means this will just be some set of vectors, beta k, alpha k, which are orthonormal. And the same will happen here. I get a set of vectors beta k on B, which are also orthonormal. So what I achieved is that I rewrote my state in this form here. Where both the alpha k form an orthonormal system and the beta k form an orthonormal system. The different orthonormal systems, they live in different Hilbert spaces, right? There's no way to compare them. Now, the big difference to here is that there's only one summation index, right? So we basically have degrees of freedom which are just correlated one with one. And the pKs tell us how strongly they're correlated. And because it's a normalized quantum state, indeed, these form a probability distribution, right? So P1 plus the maximum P we have is 1. Now, recall what we wanted to do is to characterize what happens if we do local unitary transformations. And one thing we see is that local unitary transformations can completely change the alpha k and beta k. So alpha k and beta k hold only information which can be changed locally, no information about quantum entanglement, about non-local correlations. On the other hand, the pk are actually just the eigenvalues of the reduced density matrices. So say if I trace the second system, my reduced density matrix, because a beta orthonormal will just be sum over pk alpha k. And these are orthonormal, so the pk are exactly the eigenvalues. Now, what does it mean? I have Alice and Bob. Alice does, or Bob does a local unitary transformation. This will not change Alice's reduced density matrix, which means it will not change the pk. So the pk cannot be changed by local unitaries. So it means the entanglement properties are precisely stored in these pk. I didn't actually say this is called the Schmidt decomposition. Up here, I don't want to move this board. Schmidt decomposition. And in particular, the pk are called the Schmidt coefficients. And what we see here is that the information about the quantum correlations, the entanglement, is precisely in the Schmidt coefficients. Under local unitaries. And then we have to see what we can do with other operations to these pks. So basically, if I have some state psi, this is supposed, well, so up to local unitaries, it's really just characterized by these pk. So I can think of this as some state which just depends on a vector of the Schmidt coefficients, so on a probability vector, right? Because the basis alpha k and beta k is not relevant. I can change it locally. So if you wish, you could think of this state here, right? Sum over square root of pk, k Alice, k Bob. Okay, so if we want to study what we can do, it's sufficient to look at these states. And we can assume that the probabilities are ordered descendingly, for instance, if this makes our life easier. Okay. So what can we do in this setting? Well, we can do any set of local operations and classical communication. Now, this is still a pretty general set of operations. As I said, in principle, one has to go for an infinite number of rounds if one wants to understand what can be done. Now, a remarkable thing is the following result. If we run an LOCC protocol in a pure quantum state, so any LOCC protocol on a pure state psi can be replaced by well, maybe I should briefly say what is the most general measurement. Let me maybe just make a quick remark. So if we look at LOCC, we have to apply measurements, right? Or at least we want the ability. So the most general measurement, it's what is also known as a POVM measurement. So it's characterized by a set of matrices MK, which have the property that they satisfy the condition MK dagger MK is the identity. And they act by taking a quantum state and mapping it to MK times psi, where the norm of this state is exactly the probability, the norm squared. And this ensures that if I sum that up, I actually get 1. So it doesn't have to be a projective measurement, but these are equivalent if I allow for additional quantum systems. In particular, bipartite setting, of course, it means that this would be something like MK on Alice's system, tensor the identity on Bob's system if Alice does a measurement, and vice versa. Now, what happens if we look at these protocols? Well, it turns out that the most general thing we can do can be reduced to a much simpler protocol if the state on which we act is pure. Namely, Alice starts by doing a measurement characterized by a set mk. She gets an outcome k, which she communicates to Bob. Bob does a unitary which depends on that outcome. And that's it. This is as general as any such protocol. And since this UK is just a basis transformation, a unitary one, which we saw doesn't change the entanglement at all, we can really just restrict to what this mk does. So we want to consider protocols which take psi and map it to mk tensor identity times psi for a set of measurement operators. And that's the most general thing we can do to an entangled quantum state up to this local unitary. I'm happy to explain how this works, but it probably takes 2 or 3 minutes. I'm not sure. I can also postpone it to later. If someone wants to know it now, you want to know it now? Yes? OK. Good. So basically, what we would do is we would work in the Schmidt basis. So we would work in this basis here. And now let's say Bob does a measurement in that basis. So what Bob would do is that Bob does, so Bob applies some operation M, which, well, it's indexed by some k. I will omit the index k, right? It's just for one specific measurement outcome. So Bob does an operation M, which I write out in this basis. Sorry, Bob's basis. So what does this operation do? Well, it will take this state here and it will transform it to sum over k, square root of pk, alpha k, and now beta k gets mapped to some beta I with an mik here. And well, I have to sum over I as well. Now, let's assume that Alice applies a very similar operation, namely this operation, sum over mij, alpha I, alpha j. Then, so this is what Bob does. If Alice does the same thing, what will happen? I will also get a sum over k and I, square root of pk, mik, but now I have alpha I and beta k. So all what happens, if I want to relate these two states, how are they related? Well, they're related by exchanging I and k, which means I must take this coefficient matrix and transpose it. Now, if I transpose it, it has the same singular values, which means it has the same Schmidt decomposition, and where the Schmidt decomposition fixes everything except for local unitaries. So it means that whenever Bob does this measurement, Alice can simulate it by doing this measurement. I mean, they know what state they have, right? They know the Schmidt basis. And then correspondingly doing this transpose, computing the singular value decomposition, and updating his knowledge how to transform the basis. So basically, the point is that Alice can simulate any measurement of Bob. Does this make sense?
That makes sense, but does it imply maybe that in your program, you're playing N1?
Well, it implies that Alice can do all the measurements, right? And I mean, you could wonder, there could in principle be a continuous measurement with a continuous set of outcomes, right? But this. Exactly, yeah. So yeah, I mean, you get more outcomes, right, potentially, but that's the only thing which could happen. Yeah. It's not a transpose, it's the same thing. The Alice and Bob thing are defined exactly the same way. It's magic. No. I'm saying that the coefficient matrix of the state here, this matrix here, is the transpose of this one if I get my indices right? So if I change k and I here. So the coefficient matrix of the state in a fixed basis, alpha k, beta I, are transpose of each other. But the POVM itself is the same. But indeed, it's an important thing to make sure that the measurement you do is still a POVM, which I think is easier this way. The other argument is just to say you take a maximally entangled state and write any state as A times the maximally entangled state. and then you push the measurement to the other side, but then A is in the way, and it feels a bit more tricky to see it there. Okay, more questions? Now, this is an extremely strong result, right? I mean, a reason why entanglement theory is so difficult, even in the mixed bipartite case, is that it's extremely hard to characterize this class of operations. Well, I mean, I still have to show it's a measurement, but it's actually the same operator, right? It has the same matrix elements, in one case in the alpha basis, in one case in the beta basis. So it will satisfy the same properties up to the subtleties. If the Hilbert spaces have a different dimension, then you have to, do this dirty but straightforward work of saying what happens in the orthogonal complement of some space. I mean, there's some small subtleties, right? But they're really more in the case where you embed things in a bigger Hilbert space and they have different dimension and they're easy to take care of. More questions? Okay, so what can we do? So this really tells us all we need to do is to ask what can Alice do with some measurement. The communication is still important, right? Because in the end, if they actually want to prepare a certain state, Bob does have to do the unitary. Right? I mean, teleportation doesn't work without that and so on. But if you just wonder what manipulations can we do, it's sufficient to look at what happens to the Schmidt coefficients, the Schmidt decomposition by measurements on one side. Okay. So let's do some examples to build some intuition, what we can do.
After you made a measurement, states were pure.
Okay, no, I mean, I want to make measurements which leave it pure, which are indeed these where did I put it? Probably on this part. Right, I mean, the idea is that the measurement takes psi and maps it to mk psi. In principle, the most general measurement you could do would involve some averaging over a couple of outcomes ki, okay? And then you have a mixed state. You don't want to do that. I mean, we want to have pure states at all times. But basically, whenever you get a mixed state, you discarded some information you could have as well kept, right? Mm-hmm. Yes.
You observe the value of 10.
Yeah, of course, you need to. No, of course you observe it. I mean, Alice has to store it for sure.
For each value of 10, you start from this. Yeah.
If I average. Well, I think we'll see with an example where this is important. Maybe let's let, if it's still unclear in 5 minutes, feel free to ask again. I hope that the example will clarify that. Okay. Example 1. So I have two states. Let me call them phi 0 and phi 1. So in my other notation, this would be a psi with two Schmidt coefficients 1/2. Right, so this is Alice and Bob. I just worked a bit more compactly. And then we have another state, phi 1, which has Schmidt coefficients 2/3 and 1/3. Okay, so maybe let's try to see if we can take psi 0 and manipulate it so we get psi 1. So what could we do? Well, what we want to do is basically to enhance the amplitude of the 0 state, right? So Alice would like to do a measurement which enhances the amplitude of the 0 state. So one outcome of the measurement should correspond to an operator M0, which, for instance, is of this form. Right? This should give a factor, well, this is twice as big as this, right? This would give a factor 1 over square root of 2 to that configuration. We could try doing that. So what would happen? Well, we would apply M0 to phi 0. And we would get, well, this is in the 0, 1 basis, right? So it applies a factor of 1 to this configuration, a factor of square root 1/2 to this one. So you see, if Alice does this measurement, if she gets outcome 0, indeed, the state Alice and Bob share is proportional to psi1, phi1. So they did succeed in converting that. Alice has to communicate that she got the correct result, and then they have the right state right away. Now, of course, we need to complement this to a measurement, right? So we need a second operator with that condition that M0 dagger M0 plus M1 dagger M1 is the identity. So we could choose something like this, 1 and square root 1/2. That definitely works. Now, the problem is if we apply this, it will completely remove the 0 state, right? We will only stay with this state. So M1 phi 0 will result in square root 1/4, 1, 1, which is not an entangled state at all. So we did manage to convert it, but only with some probability, 3/4 or so. So we might wonder, is this the best we can do? And the thing is, we can do better. And the reason why it went wrong is we were too greedy. We tried to get all of this state here immediately. And that's not the best we can do. We have to split up things more wisely. So what we want to do is the following. We want to pick M0 equals what? 1/3, 2/3, I guess. Yeah. So these operators also satisfy this condition that M dagger M sums to the identity. And they also have this property. This one has a property that gives twice away to the first basis state. Right? So applying this one will give me an outcome state, which is what? 1/2, 2/3, square root 1/3. So 2/6, if you wish, 0, 0. Right? Which is a correct state up to rescaling, up to normalization. And in case the measurement outcome is this one, the opposite will happen, right? So we get 1/3 and 2/3, but the other way around. So in this case, we get this state here. Now, that's not the desired state, even up to rescaling, but it has the right Schmidt coefficients, right? If we rescale it, again, has Schmidt coefficients 2/3 and 1/3, right? This term is twice as big as this one. This is all what matters. So what does it mean? Well, it means that we have to flip the bits. Both Alice and Bob have to flip their respective bits. So in that case, Alice now definitely needs to communicate the measurement outcome to Bob if they want to end up with a state phi1 here. Right? If the outcome was 0, nothing, they don't have to do anything. If the outcome is 1, both Bob and Alice flip their bit. If you want to include it here, include it in the measurement, right? The measurement would automatically flip the bit to outcome 1. So it's essential that the outcome is communicated. And what we see here is that this works deterministically, right? So we have a deterministic protocol. From the state phi0 to the state phi1 under local operations and classical communication. Now, this approach with these kind of operations is sometimes called filtering, as they kind of filter the weight of different configurations. And I mean, let me give a graphical picture. I think it's very intuitive. What did we do? So, sorry? Sure.
We say measurement M0, for example, what does the Alice read out for the outcome?
Well, she gets 0 if you wish, no? I mean, the question is, what do you call a measurement? Then we can talk about that. I mean, the most general measurement is indeed a setting where you apply a set of operators mk to your state, and they must satisfy this completeness relation, that sum over mk dagger mk is the identity. This is equivalent to the following setting where you take your quantum system, you add an auxiliary system, you apply some unitary, and then you measure this unitary, and you get an outcome k. Then this will be exactly mk times psi on outcome k, where mk has the following this matrix, if you write it kind of in this basis, has exactly m0, m1 to whatever the largest outcome is, n-1, as its first block column. And the completeness relation exactly tells you that these are orthogonal vectors, so you can complete it to a unitary, right? That's one way to see that. And it's the most general measurement, right? Because whatever you do has to be linear, and that's the most general linear thing, which has a positive outcome probability and norm 1. Mm-hmm. Yes, but I mean, it's important. So what Alice can do, right? So we need that mk dagger mk is the identity. So what Alice can always do is that if she has a measurement mk, she can replace it by some unitary vk times mk, which will satisfy the same equation, but includes that already, right? So you can incorporate it in M. More questions? Okay. Right. Okay, so let me try to give some intuition what's happening here. Some graphical intuition. So it's all about the Schmidt coefficients, really, right? In some sense, we're talking about classical probabilities. So what we have is that we have two states. We have phi 0, and this has two Schmidt coefficients, which are both 1/2. And then we have phi 1, where the two Schmidt coefficients are 2/3 and 1/3. And what we are doing here with these measurements is we're kind of slicing this up. We're taking 2/3 of the first probability and 1/3 of the second in one case, which means we're taking, well, 2/3 of this, 1/3 of this. That corresponds to one measurement outcome. And the other measurement outcome amounts to taking the rest, right? So 2/3 of this, 1/3 of that. And indeed, both of these are of this form, right? Both of these distributions. They're just kind of permuted. So we want to cut this up. We want to cut this distribution into this distribution. And that's what we achieved with this measurement. Or if you wish, we can do the opposite. We can say, can we patch this one together from the right one by permuting the entries in some way? So if you find this graphical calculus reasonably convincing, you can immediately get an intuition, at least, why the opposite transformation is not easily possible. So if I want to do the reverse transformation, I would take this 2/3, 1/3, and I would try to go to a situation where both probabilities are equal. And now you can easily convince yourself that whatever you do, you can do a greedy strategy. You're always left with something where, in the extreme case, you indeed just have a state which has no entanglement whatsoever. And I mean, you can formalize this. This indeed tells you that the maximum success probability in the converse direction is 2/3. It's the maximum of this distribution you can fit into this one. I mean, the same intuition you can use to convince yourself that there are states which cannot be converted into each other in either direction with unit probability. So example 2 would be something where, say, one state has 3 non-zero Schmidt coefficients, 3/4, 1/8, 1/8. And the other one has 1/2, 1/2, and 0. And we might wonder, can we convert between them? So we would have this 3/4, what is it, 1/2, 1/4, something like this, right? And we would like to make something which has 2 equal height blocks. And again, you can try playing around with it. So for instance, you could take these two and piece them together, right? And then you take these two and piece them together. But you see there's still a failure probability. It will work for a while. If the 3/4 wouldn't be 3/4, but a bit smaller, it will still work. Like 1/2, 1/4, 1/4 would work. But this one doesn't work, not in this direction. And the opposite conversion cannot work because the rank of the reduced density matrix here is 2, right? There's only 2 non-zero Schmidt coefficients. And whatever Alice does, it will not increase the rank of Bob's density matrix unless she mixes measurement outcomes, but then they don't have a pure state. So neither direction is possible in this case. So it means that the conversion of entangled states into each other, in the case where we take one copy of one state and want to change it to one copy of another state, it gives us a partial ordering on the set of states, but really only a partial order. Okay. Questions? No, I didn't talk about entropy at all. No, and it's also not correct. Okay, so we have to see. I wanted to talk about the asymptotic copy case. So I might have to cut short, but maybe let me just mention that one can formalize this condition. So basically what we have is we have 2 probability distributions here, P and Q. And if we can piece one together from the other, this means the following. It means we can take the distribution P and write it as a convex combination, as a mixture of permutations of Q. So this is a permutation, and that's some probabilities. And whenever P can be expressed in this form from Q, it means that we can convert a quantum state with these Schmidt coefficients and no. Okay, so what is this? This is basically, Birkhoff's theorem tells us this is exactly a doubly stochastic matrix. So it's a random process which moves it towards a maximally mixed state, or vector, which in case of entanglement is a maximally entangled state. It's completely flat. So it's the most powerful one. So it is this direction, correct? Correct. It's always a bit confusing, I agree. One is always tempted to write the opposite direction, in particular because there is this nice characterization when this holds. And this holds exactly if the following holds, namely the partial sums of the PI are smaller or equal than the partial sums of the Ks of the Qs, where these vectors are ordered descendingly, as I said in the beginning. So if this holds for all K, which is known as majorization and usually written like this, with some curly brackets, So if this relation holds under distributions for all k, then and only then it can be written in this form, and then and only then you can deterministically convert a state with these Schmidt coefficients into a state with those Schmidt coefficients. It's not hard to prove, but it would probably take 5 minutes to give the intuition, and I'd rather keep this either for the end or for an informal discussion afterwards to have enough time for the asymptotic case. I think that's valuable. Now, one thing I would like to mention, because I wanted to get to entropies, is the so-called notion of Sure convexity or Sure concavity. So this condition here, which is short written like this, tells us when we can convert a state with certain Schmidt coefficients into a state with other Schmidt coefficients. They have to be ordered descendingly, both of them, right? The entries. Maybe I should make it remind you indeed. I imposed this in the beginning, right? So these are both ordered. Now, an important thing is that if we have a function on some vector p, we say it is Sure concave if the following holds, namely if Q majorizes P, then F on P is larger or equal than F of Q. Now, on the other hand, as I just told you, this majorization is exactly equivalent to the fact that we can convert between these states, right? So this is again equivalent, right, to this conversion here. So what does it tell you? If you have a function with this property, the Sure concavity, then it means that whenever you can do an entanglement conversion on the state, it will decrease the value of this function. So it's something we would call an entanglement measure, right? Something which tells you something about the amount of entanglement. And an important fact is that all entropies, so the von Neumann entropy, but also all Renyi entropies, are Sure concave functions. Again, it's easy to show. It's 2 or 3 minutes to sketch it, but I'll leave it for the end if someone is interested. Let me. Well, but I mean, if you can do the conversion in both directions, if you believe this majorization condition, it means this must hold in both directions, which means that all the partial sums must be equal, which means that all the p's and q's must be pairwise equal, right?
Oh, this is the
Sorry? No. This is an if and only if. I mean, this is all if and only if, right? So this condition is equivalent to being able to write this, and this is equivalent to being able to convert the state.
Yes, but in your first example,
Sorry?
in your first example,
Well, it's about deterministic conversion, right? This is deterministic. There's a generalization of this condition for probabilistic conversion. So basically, you have to say probabilistic means that there's also another outcome, which also has Schmidt coefficients. So you have a set of outcome probabilities with corresponding Schmidt coefficients, and then you have to average these sums of ordered vectors with these outcome probabilities. Then that also applies. But then there's a degree of freedom, because typically the garbage, you don't really care what you have sometimes. So it's a bit harder to check, right? Because you have to make a smart guess what the best useless output is. Okay, so these functions are all Sure concave. This doesn't really tell you that entropy is a perfect measure of entanglement, but it tells you something about entanglement, right? If you can take one state and convert it into another one, the other state will have a lower entanglement. Or conversely, if one state has a higher entanglement than another one, you can't convert that state into the one with the higher entropy. But this is not an if and only if. You can find examples where these entropies are all bigger, but you can't convert between the states. Questions? Okay, let me see how to split the time. Okay, so in some sense, the situation is very complicated for single copy conversion because all these coefficients matter, right? And there's many cases where you can't convert between states, or where you can only convert in one direction. So if we go back to this example, for instance, you could say, well, I could go in, what did I say? So in one direction, I can at least go probabilistically, right? I can take this state and go with some probability larger than 0. In the opposite direction, I can never go because this would require increasing the number of non-zero Schmidt coefficients, which is not possible. Now, on the other hand, we would say this state has quite a bit of entanglement, right? I mean, it's maximally entangled for 2 qubits. Now here, I can take this example and push it to the extreme, right? I can put some epsilon here. So if epsilon is very small, this is very close to a product state, right? Nevertheless, if I would say that at least probabilistic conversion possibility or ratio of probabilities is maybe a useful measure, it would tell me that this one is much more useful than the other one. But that's intuitively not true, right? If I want to do teleportation of 1 qubit, this is perfect. This one is not very useful. So it's a bit unsatisfactory to look at these conversions and try to get an actual number out of it, which tells you how valuable a state is. Now, how can we overcome this? We can overcome this by taking more than one state and asking, what can we do, say, if we have several copies of a quantum state? So if we stick with that example, and say we would take 2 copies of this state here. So the total probability vector or Schmidt coefficient vector would be 1/4, 1/4, 1/4, 1/4. This is maximally entangled, which means I can really slice it up into anything, right? Because I can take all permutations of what I want. So in particular, I can get this example I had before. Sorry, 3/4, 1/8. 1/8. Suddenly, if I take 2 copies of the state on the right, I can deterministically produce this state. If you want, you can easily convince yourself you can take these, permute them, and piece that together. For instance, if you take all permutations, it will definitely work. I mean, you might want to put a 0 here, so you have the same length. Of course, it's a bit unfair. We took 2 copies of that, and we asked about 1 copy of the other one. But if we're doing the opposite, we could also do the opposite. We could take 2 copies of this state, which only with some probability gave that state. Now, if we take 2 copies, the largest coefficient is 9/16, which is larger than 1/2. So already at the first point, it tells us that it will not work. And so we will never be able to get this state here, even a single copy, because a single copy requires 2 equal weight coefficients, but this is bigger than 1/2. There will be no way that we get away with that. So suddenly the situation has reversed with 2 copies, right? 2 copies of this state are actually more powerful than 2 copies of that state with a 3/8. So several copies will change the picture. And the idea is if we go to more and more copies, maybe the picture might get simpler again. And that's indeed what happens. And I would like to give an intuition how this happens and why the entropy comes out as a good entanglement measure. And I hope half an hour should be enough for that. OK. So another thing we might want to consider is that maybe we don't want to be perfect. Now, if this epsilon is very small, maybe if we set it to 0, we make a small mistake, right? So we might tolerate it. If you take several copies of this state, you get epsilon to a high power. That's even less likely, right? So you might just drop certain states and say I make a small error if I drop them. If this error in some nice way goes to 0, we might actually be fine. So so what are the rules of the game? So in an asymptotic setting, asymptotic entanglement conversion, we want to do the following. We have one state with a set of Schmidt coefficients, another state with a set of Schmidt coefficients, Q. We want to take some large number of copies of one state and of the other one. And we ask, can we convert between them? And there are several things which are important in this setting. We want this to work well as we take n and m to infinity. And you'll see in a second how we want to take them to infinity. So in particular, we want that the conversion rate is non-zero. So there is some rate for converting in this direction, another one for converting in this direction, which is the corresponding limit for n and m getting big of the ratio, the best ratio I can achieve. I mean, maybe it's m over n. It depends what you call the rate. Right? But it's basically asking how many copies of n per copy of m can I get or will I obtain or will I need in such a protocol. But this is meant in a way where I make n and m big. So I can have some losses, but the losses in some set should be sublinear or as small as possible. If you want to formalize it, you really want to say that for every epsilon below my target, if I make n and m big enough, right, I will get as close as I want to that. So we want a success rate which approaches some value as n and m get big. We don't want it to be exactly correct. We will be happy, and that's a big change. We only want it to be approximately correct, meaning that our output gets delta close to the correct one as n and m get big for any delta larger than 0 again. And we want this in a global error measure, which is an extremely strong condition. We don't want the individual states to be close to what we want. We want the overall n-fold tensor product to be close to what we want. That's very strong. And in principle, we only require that this works with a very high probability, again, approaching 1 as n gets big. Now, this is not strictly necessary, because if we allow for mixed outputs, if the protocol fails, we can just output a random state, and we will be good, right? Because if this happens with probability going to 0, this is just part of this delta here. So this we don't really need to take into account. But this is essential, and one reason why it's essential is that the only way to increase the Schmidt coefficients, right, is to drop stuff, right? If we want to go from this one to this one, if we want to do it exactly, we will need quite a lot of these maximally entangled states. But if we drop small epsilons, we might get away. And the goal, and that's what we will achieve, is actually that these two rates goal means we will achieve this. The rate in one direction will be equal to the rate in the other direction, meaning conversion becomes reversible. And this rate will be exactly measured by the entropy of P versus the entropy of Q. Von Neumann entropy. Okay, so what's the intuition? Let me illustrate it for qubits, but the argument is really completely general. I'm not even sure it's easier to write it for qubits.
What's the definition of closed arrow means?
Okay, so I want two types of protocols. Now I want one protocol where I start from many copies of this state, and I want to prepare some other state. And then I can also, well, I mean, as we saw in some cases, we can go with probability 1 in one direction and with small 1 in the other, or 0 probability in the other one. Here, of course, we don't want probabilities, but it could be, that I take one copy of the maximally entangled state, I get one copy of another. I mean, the probabilistic one would work like that, right? I can take my single copy protocol from 1/2, 1/2 to 2/3, 1/3. On many copies, I could just run it, right? In one direction, it succeeds with probability 1, so my rate would be 1. In the opposite direction, it succeeds with 2/3 probability. My rate would be 2/3 if I just run it many times and output whatever number of copies I get. Right? I will get an expected number of copies, which is 2/3 of what I put in. So this would not be reversible, right? If I go back and forth every time I lose 1/3. Whereas if it would be reversible, it would be a much more meaningful number, right? Because it will really mean in the setting of many copies, and let me stress it now already, right? That's where entropy makes sense, in the setting of many copies, which you typically don't have in a many body context. So it's a bit questionable how strongly one should stress that role. This can be made reversible. Yes. Well, then one is the inverse of the other, no? I mean, the way we do it is to actually prove something different. Namely, we try to go to many copies of this state. Right? Because if we understand how this conversion works, right, we go to a maximally entangled qubit state, 1 bit. If we know how to do this, and then we also know how to do this, obviously, in both ways, then we can do this by going via this, right? And if it converges to something reversible, we won't lose, well, asymptotically at least. And in that case, indeed, the rate, right, in this case, you would say that the rate is the number of maximally entangled states per copy of n you need, right? So the correct definition would be that the entanglement of the state on the left is amounting to the number of maximally entangled states, right here, which you either get out or you have to put in to produce one copy of this state, or which you can get out from one copy of this state. Right? So if you talk about, I mean, you want this ratio, not the opposite ratio. Yeah. Global fidelity, global distance of your favorite kind, no? I mean, that typically is the overlap of the wave functions. I mean, there's potentially a dimensional factor. One has to be careful because one takes a limit of n going to infinity. But the way the proof is done is in terms of overlap of the wave functions. But I mean, that's kind of the strongest measure you can take, right? It's equivalent to the two-term distance. OK, so let me try to give the intuition. See how far we get. The thing is that doing the deltas rigorously is not very hard, but much more tedious than kind of hand-waving a bit around them. So what is the idea? So let me take some qubit state, psi, which has, well, p of 0. Oh, p of, p sub. Let me write p of because I wrote it like this in my notes. I guess up to now this was p sub 0. Now, if I take n copies of this, what do I have? Well, I have a sum over x1 to xn, then some p x1 to xn, and then I have a vector x1 to xn here, which I can call x in short for Alice, and the same x for Bob. Now, what is this p? Well, it's just a product of p of x1 times p of x2, and so on. Now, if you want to formalize what happens, you can take the log of this and observe that this is a sum of the logs of the p's, which means it's an average of some IID source, outputting p of x, or p of something. Now, I won't do that, but this definitely immediately gives rise to the entropy and all central limit theorems you want. But what's the intuition? OK, so what we do is that, say, Alice, thought experiment, measures x in the computational basis. She doesn't want to do that. That will break all the entanglement. But now let's ask, what's the probability for a certain outcome? Well, it's just this p x1 to xn, right? Which is a product of these probabilities. Now, what do we expect to get? Well, the most likely one, let's say p of 0 is bigger than p of 1, the most likely individual outcome will be all zeros. Is that what we would generally expect? You know, you toss a coin, it's biased. Three halves heads, 3/4, what? 2/3, no, 2/3 heads, 1/3 tail. No, you would expect on average 2/3 of the coin tosses are heads, 1/3 tails, right? So a typical outcome would have a number of zeros, which we call n0, roughly around p of 0 times n. And the number of 1 outcomes would be roughly p of 1 times n. So the probability for an outcome we would typically expect, what would be the probability of such an outcome? Well, it would roughly be the probability of 0 times the number of times the outcome 0 occurs. Sorry, to that power. So to the power p of 0 times n times p of 1 times n1. So p of 1 times n. And this is what? Well, this is 2 to the minus n times minus p0 log p0 times p1 log p1. The logarithm is the natural basis, namely 2. So what you see is that the thing in the exponent is just the entropy. Right? This is just the Shannon entropy of P, which we had up there. Guess I erased it. Okay. So actually, a picture is quite instructive. So if we write the expected number of zeros, we can plot the probability to get a certain number of zeros. This will grow exponentially. Right? That's a probability for a certain outcome with n0 zeros. But then the number of such outcomes is a Gaussian centered around 1/2. Right? That's a number of such possible x zeros, which have a certain number of zeros. If you multiply the two, you will get a displaced Gaussian, right? And well, the central limit theorem tells us that we will get very close to the average, right? So we will be very close to this interval. It's actually more instructive, so not in the first try, to actually draw a logarithmic y-axis, right? Because then it's much simpler. We have a linear growth of the probability. Right? That's log p or log n, log of the number, and the log of the number is a parabola. And the peak of the product is exactly where the two have the same slope, so somewhere here. So what this tells us that we will be in a narrow strip here. Now, in the light of time, I mean, so what is one doing? Basically, one is saying, well, let's zoom into this picture here. Let's maybe shift one of these lines. So what we have is that we have the number, log of the number of possibilities. And then we have the probability. I shift it. And now we have the expected value for the probability. And we look at an epsilon strip around this expected probability. So we look at the situation where the probability for outcomes is in the regime 2 to the n times h of p plus minus some epsilon. This is what is called an epsilon typical subspace. And then we can ask, how many possibilities do we have in that subspace? And that's basically, well, we know that with probability 1, we will be in this regime. right? As we make n bigger, the central limit theorem says this will get narrower and narrower. So the probability to find an outcome x whose probability deviates by more than this epsilon is going to 0, right? So with probability 1, we will be in this typical subspace. Now the coarse picture, it's a bit a lie. No, the coarse picture is that basically all expected outcomes, these typical outcomes, have more or less the same probability. It's of course not true. They differ by 2 to the minus n times epsilon, which is very big. But compared to how different they could be, they're very close to each other. At least on a log scale, they're pretty close. Now, how many of these are there? So how many such x are there whose probability is in this regime? Well, the probability to have, I mean, these probabilities must sum to 1, right? Or 1 minus some very small delta, because the probability to not get one of these results is going to 0. Which means that the total number, let me call this z, is somewhere in the interval 2 to the n h of p plus minus epsilon. Okay, so what does this tell us? So it tells me that, well, if I restrict this sum here to those x's whose probability is very close to this typical value, I will not change my state a lot, right? Because these probabilities basically sum to 1. Whatever it's outside for big N is going to 0. So I can take this state, psi tilde, so these are typical, epsilon typical actually. And this state is as close as I want to the actual target state, right? But it has much less non-zero Schmidt coefficients. But the number of non-zero Schmidt coefficients is not 2 to the n, it's 2 to the n times the entropy, roughly. Which means that if I take a maximally entangled state with that number of non-zero Schmidt coefficients, I can prepare that state by the argument of cutting up the probability distribution, right? I mean, whatever it is, it will not be entirely flat, so it can be prepared from something with the same number of Schmidt coefficients, but completely flat. Oops. So it can be prepared from a maximally entangled state where all the coefficients are equal, which is summing to, oops, sorry. Which is summing to 2 to the entropy. One can be clean about the epsilons. So what does it mean? Well, it means I can take, oops, there's an m. I can take n times h of p copies, right? About what? 0, 0 plus 1, 1. And n times h of p copies. That's one direction, right? So I can start from a maximally entangled state, take n times h of p copies, plus epsilon if you want to do it cleanly, and obtain this state, which again is delta close to the state I actually want. To go in the opposite direction, there's different ways. The simplest way to go in the opposite direction is to say, well, let me take my original state and actually do a measurement which projects onto subspaces with a fixed number of zeros. Then I will again end up in these typical subspaces, right? I know that with high probability, I'm in a subspace where the number of zeros fluctuates only very little. How much entanglement will I lose? Well, if the dimension of all these spaces would be the same, it would just be a factor n, but it's an exponentially big space, right? It has dimension 2 to the n times the entropy. I divide by n, it's basically the same number. If you contemplate about this a bit, you will notice that actually the number doesn't fluctuate too much compared to what you can lose. So it fluctuates basically by an epsilon again. So the converse direction can also work exactly the same way. You can do it a bit smarter and keep a bit more of the entanglement, but asymptotically it doesn't matter. Okay, this can be made fully rigorous with all epsilons with not so much extra work, but a bit of extra time, which we don't have. So the bottom line is the following. Let me maybe just write down the bottom line. So in an asymptotic setting, we can take any state psi with Schmidt coefficients p, right? And convert it reversibly into a number k of copies of a maximally entangled state. If k over n is equal to the entropy of p, or if you wish, the von Neumann entropy of the reduced state of the state. And that's why the entanglement entropy is a good entanglement measure. It allows you to assign a unique value in terms of entanglement to a given pure bipartite quantum state in a sense which is really reversible. It's unique, right? Whatever states you have with a certain entropy and other states, if I give you many copies of them, you can go from one to the other, and your loss will be sublinear. So it will vanish asymptotically per copy. In that setting, it's a great thing. It's very much resemblant of classical information theory, right? Compressing random sources and so on. But it's specific to this setting, so one should be a bit careful also, how much value one gives it in other settings, where it's maybe not natural to look at many copies, like maybe in many body settings. And yes, with this, I guess I'm at the end. Thanks for your attention.
Thank you, Norbert. Are there any questions?
So if you have now three systems which are entangled, is there some analog of these quantities which it would tell if these three entangled system can be turned into the other ones? For Bipartite.
Well, three is more complicated, right? You can't generally convert different states.
But are there some set of numbers, like entanglement entropy, some set of numbers that tell you whether it's possible to go with?
I doubt that you can have it from entropies, because even in the bipartite setting, entropies are not enough. Right? So if I have two states, the entropy, all including the
asymptotic sense. In this asymptotic sense, here the entanglement entropy is enough, right?
No.
This is related to this Embrex open questioning quantum information, because now instead of having like a maximally entangled states like 0, 0, plus 1, 1, I think that you can have W state, GHC state, several states, and see whether out of one you can get different numbers. And for the moment, we know that we know of the order of 5 of them at least, but it may happen that one needs infinitely many in order to be reversible. So it's at least one of the problems that is opening quantum information already for many years.
Yeah, but what is actually very relevant is that with bipartite entanglement and LOCC, you can create any multipartite state. In some sense, there's not more than a bipartite entanglement, because you can create any multipartite entanglement by doing LOCC on top of that.
But not reversibly.
But the rates are
The
not.
question is whether you do reversibly or not. Okay, so if there are no more questions, then we have a coffee break now and then the discussions.